In this lecture, we will see in detail about the identical particle. I have divided this lecture into several parts. Today, we will see the part one about the identical particle. Before going into the detail, we will see the definition of identical particle. By definition, here we are going to take two particle system, then we will take for many particle system. In two particle system, two particles are said to be identical if all their intrinsic property are exactly same. That is, property like mass, charge, and spin are exactly same. No experiment can distinguish one of them from other. An important consequence follows from this definition. When a physical system contains two particles, there is no change in its property if the roles of two particles are exchanged. This is the important fact we have to remember. In classical mechanics, the identical particles are distinguishable as we can measure their position and velocity simultaneously, and also we can trace their trajectory. However, in quantum physics, the situation is different due to uncertainty principle. The identical particles are indistinguishable. Let us consider the two cases where the two particles are far away, then there is no problem. The wave function will look like this. Here, the wave function looks like this. So there may not be any interaction if particles are separated far away. However, if particles are closer, then the wave function of particle 1 is like this, and wave function of particle 2 is like this. There is a overlapping. Here, you cannot say this wave belongs to which particle. So, you cannot really distinguish the identical particle in quantum mechanics. With that understanding, we will move further. Now, we will take the two particle system. The wave function of the two particle system can be taken as the bold letter capital psi, which is a function of r1 and r2, of course, with time. R1 is the radial coordinate for particle 1, and R2 is the radial coordinate for particle 2. Then naturally, its time evolution is determined by the Schrodinger equation, that is I h cross delta psi over delta t is equal to h psi. So this is the time derivative. If you know the initial wave function, then you can find the wave function at any other time using this Schrodinger wave equation. That is the meaning of this time evolution, where h is the Hamiltonian for the whole system. Since we have two particles, the Hamiltonian is equal to minus h cross squared over 2m1 delta 1 squared minus h cross squared over 2m2 delta 2 squared plus v, which is a function of r1 and r2, of course, with time. So here the first term is uh, the kinetic energy term. First two terms are kinetic energy. So delta 1 square is a Laplacian operator for particle 1, and delta 2 is the delta 2 square is the Laplacian operator for particle 2. And similarly, m1, m2 are the mass of the particle 1 and 2. The statistical interpretation is modulus psi squared. Psi is a function of R1, R2, and T. T cube R1, T cube R2. This is the probability of the finding the particle 1 and 2. So this is more precisely the probability of finding the particle in the volume T Q R1 and particle 2 in the volume TQ-R2. Evidently, psi must be normalized. So naturally, it must be normalized in such a way that the integral of this parameter is equal to 1. For time independent potential, let us say this potential is time independent, then we can obtain the complete set of solution by separating the variables. It's a usual technique. So here, the capital psi is a function of R1, R2, and T. Now, I am going to separate the variable, that is radial part and the time part. The radial part is small psi which is a function of R1 and R2 alone, and the time part is taken care of this exponential term e power minus I e t over h cross. So we have separated the wave function into two parts. One is a radial part and the other one is a time part. So the spatial wave function small psi must satisfy the time independent Schrodinger equation. That is time independent Schrodinger equation is minus h cross squared over 2m delta 1 squared minus h cross squared over 2m delta 2 squared plus v, which is a function of r1 r2. We have taken here that is potential is time independent, which is equal to E psi. Remember that here I have put only m, not m1, m2, because these particles are identical in nature. So naturally, I replaced m1 is equal to m2, and here the E is the total energy of this system. Now we will see about the fermion and boson. Uh, the wave function is psi 1, which is a function of psi r1 and r2 can be written as psi sub a, which is a function of r1, and psi sub p, which is a function of r2. In quantum mechanics, electrons are identical one, unlike in classical physics. Electron in quantum mechanics are identical one. The psi a represents the wave function of the particle 1 at, at the coordinate system r1, and psi p is the wave function of the particle 2 at the coordinate system r2. Here, the quantum mechanics neatly accommodate the existence of particles that are indistinguishable in principle. We simply construct the wave function that is non-committed as which particle in which state. There are actually two ways to do it. That is, psi plus or minus can be written as 1 over square root of 2 multiplied by psi a r1 psi p r2 plus or minus psi a r2 psi p r1. Here you remember that here in the first term, the wave function of the particle 1 is in the r coordinate system, particle 2 is r2 coordinate system. This is r1 coordinate system, this is r2 coordinate system. Whereas here, the particle 1 is at the coordinate system r2, because we are exchanging, and rp is not at r2, is at r1 coordinate system. This plus or minus shows that whether this wave function is symmetry or anti-symmetry. Plus means symmetry. Here also plus, here plus. Minus means anti-symmetry. That we'll see in detail. Plus is for boson and minus is for fermion. We will come to it now. Now we have seen psi sub plus or minus is equal to 1 over square root of 2 uh, multiplied by this psi a, which is a function of r1, psi p of r2 plus or minus psi a of r2 and psi p of r1. Here 1 over square root 2 is the normalization constant. Thus, the theory admits two kind of identical particle, one with plus and the other one is with minus. The bosons for which we use the plus sign and fermions for which we use the minus sign. Proton and mesons are bosons. Proton and electrons are fermions. It is so happened that all particles with the integer spins are bosons. That is, proton and mesons are having spin of integers, whereas all particles with half integer spins are fermion, like proton and electron are having half spin, so they are fermion. This connection between spin and statistics, that is, boson and fermions have quite different statistical properties. We will come to it later. Can be proved in relativistic quantum mechanics. In non-relativistic theory, it is taken as an axiom. It follows in particular that two identical fermion, for example, two electron, cannot occupy the same state. From the above equation expression, we know that psi sub minus is equal to this one. This is minus 1 over square root of 2 psi a of r1 psi b of r2 minus psi a of r2 psi b of r1. If psi A is equal to psi B, if A and B are equal, then this will become 0. So there is no wave function. Wave function will be 0. This is our famous familiar Pauli exclusion principle. That is, no two electron can occupy the same energy state. So it is not a wired ad hoc assumption applying only to electron, but rather consequence rule for the constructing two particle wave function. This is not only for electron, any two particle wave function. Applying this is applies to all identical fermions. Now we will see about the particle exchange operator. We have designated the particle exchange operator as capital P cat. When it acts on the wave function psi r1 r2, it will exchange the particle r1 at r2 coordinate, r2 at r1 coordinate. Then if exchange operator act on this outcome, that is psi r2 r1, then you will get the original state, that is psi r1 r2. So now we will see the eigenvalue of this particle exchange operator. Let us say this eigenvalue is lambda, then the particle exchange operator act on psi, you will get lambda psi. If it acts again, then p squared psi is equal to p lambda psi. So when lambda is the number you can take front in the front, then p act on psi, you will get lambda psi. So this will become lambda squared psi. That is, here we have seen that when exchange operator act twice, then we will get the original state. That is, lambda squared is equal to 1. Hence, lambda is equal to plus or minus 1. That is, psi r1 r2 will be equal to, if the exchange operator act on it, we will get plus or minus psi R2, R1. So this is about the exchange operator. With this, we will conclude this lecture. Uh, we will go further on about this topic in my next lecture. So, I have, as I said at the beginning, I have divided this lecture into uh, 3 to 4 part. We will see this continuation in my next class. Thank you very much for watching my video and supporting me continuously.